Hello, everyone. I'm Everton de Oliveira from the Groundwater project. And we offer free books, free content on groundwater. And one of the books is better than the other. And today is no exception. You should go and read the introduction to Karst Aquifers. It is a great book. I had a lot of fun reading it, really, I'm not kidding. And I learned a lot. I thought I knew something about Karst Aquifer being a hydrogeologist for so long, and I learned a lot. It's a great book. So today I have the pleasure to bring to you the authors of this very nice book. First of all, it's Eve Louise Kuniansky. She graduated in physics in 1978 and in civil engineering in 1981, and had a master's of science in civil engineering from Georgia Tech in 1982. In January 83, right after, she began a career with the U.S. Geological Survey and coordinated the USGS Karst Interest Group from 2000 to 2017. She's currently in an emeritus status with the USGS. Next author is Charles Chuck Taylor. He holds an undergraduate and graduate degrees in geology from the University of Kentucky. He's a groundwater hydrologist and heads the water resources section of the Kentucky Geological Survey. Chuck joined the KGS after a 20-year career with the US. Very good. Next is John Williams. John has a bachelor's in arts in geology from the Colgate University and a master of science in geoscience from Pennsylvania State University. John currently is the groundwater specialist for the U.S. Geological Survey Water Science Center in New York, and is responsible for technical oversight of the survey's groundwater program in the state. And finally, last but not the least, Fred Payet. He is an adjunct professor of geoscience at the University of Arkansas, an emeritus research scientist with the U.S. Geological Survey. He serves as the chief of the USGS Borehole Geophysics Research Project in Denver from 1983 until his retirement in 2002. Since then, he has had temporary appointments at the University of Maine, the University of Rennes in France, and University of Queensland in Australia. Thank you all of you for coming in today. It is a great pleasure and a prestige to have you around here today to talk to us. Great book, by the way. I enjoy reading it a lot. Thank you. So you all worked in the beautiful scenery that Karst produces. What drove you to this field of groundwater? The beauty of the dramatic scenery alone? Please tell us your ways to achieve your knowledge. Thank you very much. Welcome. Eve, you're first.
Okay, well, initially, some of my first projects were in more fluvial depositional environments, but then I transferred to the Texas office and was involved in the modeling of karst aquifers there, and that began my interest in karst, although I had an interest in caving early on, as when I was at Tech, my roommates were really big into caving. I already had a destroyed knee, so I didn't do quite the adventures they did. They used to rappel the really deep pits and do some caving that I really wasn't quite up to doing, but I would go on most of the larger caves. I really couldn't do crawl spaces. So I got sort of interested in caves back in the late 70s and early 80s, even though I lived near the Tennessee, Alabama, Georgia, large cave and karst area there. But I did not get really involved in karst aquifer systems until about 1986. And that's what got me very interested in it. And then I do love the landforms. I think if I had it to do over again, I should have been a geomorphologist, and I would do nothing but travel around the world trying to understand how these amazing landforms get created, because it's so complex. And I really encourage people to look at the cover collage on the book and then the one internal, because it gives you an idea of just the enormous variability that there can be in karst because of the variability in the nature of carbonate rocks and those sedimentary processes. And so that's when I really got heavily into karst, was I'd say 1986. And I decided actually to form the karst interest group because people had a tendency to only work in one aquifer or one area. And so that meant they weren't exposed to the high variability of karst aquifers. And so even within the USGS, we had people that were a bit provincial. And so they only understood their aquifer, and there wasn't as much technology transfer among people working with these complex systems. And so that was my main reason. And I had an ulterior motive too. We rotate where our meetings are every year. So that's a good reason to get to go on field trips to totally different areas around the US, which is, to me, the highlight of those meetings were the field trips and getting the feedback from the experts in that local area. But that's how I got interested in karst. It was partly project related, but also just caving related, and just because of the spectacular scenery all around the globe.
Good. Thank you very much, Eve. Chuck, your turn.
Yes, thank you. Well, I grew up and went to school and started my professional career as a geologist and hydrogeologist in the state of Kentucky in the USA. And Kentucky is about 50 to 60% karstic, underlain by limestones. And we are also world famous for Mammoth Cave National Park, which almost everybody thinks of when they think of karst. So I kind of grew up with it by osmosis, I guess you could say. And then I was forced sort of, if you're going to work as a geologist or hydrogeologist in Kentucky, you have to know karst. But then I also joined the USGS. It's where I met Eve, and I was able to work in a number of other states in the area, central United States, that also were heavily, had heavy karst issues. And so it was a real privilege, to be able to study, as Eve said, other karst terrains and collect some knowledge and help people do projects. When I joined the USGS, there weren't a lot of people in the USGS that actually considered themselves karst experts or karst experienced. And so even though there were a lot of people that worked in carbonate terrains, I think that was one of the things that USGS has developed over the years, is much more expertise in karst. But when I joined, you could count us on a couple of hands maybe. And so it actually opened up a lot of opportunities to work in a lot of karst terrains. And I was really privileged to be able to do that.
Very good, very good. You, Fred?
Yes, I come from a hardcore engineering background, but had always been interested in the outdoors, and ended up taking an interest in hydrology and starting out as a departmental hydrologist in Ohio. Got heavily involved with groundwater modeling, and as such was using a lot of borehole geophysics to define the parameters in my model. Got associated with people from the USGS who were doing well logging, and they encouraged me to apply for a position with the Borehole Geophysics Research Project in Colorado, and I made that my career. So I view karst as just a very difficult well logging problem. It's qualitatively no different, just quantitatively much more complicated. And the basic problem is you get to see what's in the borehole, but it really only applies to a couple of borehole diameters around the point where you're making a measurement. The fact of life is that when you push water into or take water out of a borehole, most of the resistant loss occurs in that convergence zone. And so the permeability or the transmissivity you detect at a specific karst location is not really representative of the whole feature. And I quickly cited numerous circumstances where you have two nearby boreholes, they both penetrate exactly the same bedding plane open on solutions, one of which produces water, the next one doesn't. So you realize that it's a much more complex problem than typical sandstone aquifers that you can project reliably from one borehole to the other.
Yeah, yeah. Okay, thank you, guys. I like the viewers. John Williams couldn't make here today, but you have an opportunity to see him as he has a borehole geophysics book that is going to be released soon, and you can see the interview there. So we'll keep going, guys. By the way, I read your book, and it was, I liked it a lot. Once I had the opportunity once to travel the coast from Croatia down to Montenegro. It's all
Beautiful.
car. I rented a motorcycle, there. And, as a geologist, I thought I knew Karst. And then I read your book. I said, Jesus, how ignorant I am. I have to redo the trip. Thank you very much for, opening my eyes. So a question for those who are not familiar. If someone doesn't know, what is Karst and why is it important to study it? Just as a beginning to start the interview.
Chuck, do you want to answer that, or who wants to answer that question?
You're the lead author, Eve. I think starting off all these questions.
Okay, well, I'll point then. If you're, go.
Well, there's two aspects. There's karst terrain, which is a terrain in which your surface water disappears underground. And then, of course, there's the karst aquifers, which are where you have a saturated, unsaturated zone that has mostly carbonate and evaporate rocks, where the rocks dissolve and create these very fast moving waters. So there's a little bit of a distinction between karst terrain versus a karst aquifer. And they are some of the more difficult aquifer systems to study, because you have the issue of your surface water disappearing underground, possibly the incoming water into your aquifer system doesn't follow your surface topography all the time. And it also changes depending on how high the water level is, owing to the development of these different flow paths as water tables stay in a certain area, because the fluctuation of the water table helps aggressively dissolve water in bedding planes. Sometimes first you have the vertical downward movement, and so these aquifers get very complicated. They can have, normally, you might have flat laying sedimentary carbonate rocks, but then you can have structural deformation that helps create vertical fractures a certain way. And so that's part of the reason why the terrain is so variable around the world, is you've got your deposition of your carbonates and evaporites, then you have post-depositional structural changes, and you have these rocks exposed over time to different climate regimes. And all those factors create the enormous variance in how these rocks look and in the terrain itself versus how the aquifers function. And so it takes a lot of effort, more so than your typical sandstone or alluvial aquifers, to understand both how your terrain evolves and how your aquifers evolve. Was that a good enough answer?
No,
Chuck, y'all want to add anything?
Sure, Chuck. What's the importance then of studying karst aquifers?
Yeah, I'll come back to it from the perspective of as a hydrologic resource. It's globally distributed. Karst is everywhere across the globe now. It only accounts for about 13% of the world area, the surface karst, but where it occurs, it's used by about 20-25% of the world's population for water supply. And because in karst areas, there's a very dynamic interconnection between the surface and the groundwater, karst aquifers are very important, not only as aquifers, but also as contributors to surface streams and surface water bodies. Karst aquifers provide a lot of important water supplies wherever people, live and work. They're on mountains, they're on coastal areas. They're all over the place, all kinds of different physiographic regions. And then not only that, but they're also a habitat, a unique habitat for a lot of protected and endangered species, aquatic species as well as subterranean species. So there's just a lot of aspects to the karst as a resource that make it really important and make it important for us to study and understand properly.
Oh yeah, and another issue is that they're extremely vulnerable to contaminants from the surface. So that's why often the outcropped areas or subcrops of karst are mapped and protected to help prevent contamination of the water resource.
Very good. Fred, you want to add something?
Yeah, I've been fascinated by the many different facets of karst that you can run into. I was involved in a project in Kuwait City where the subsurface was gypsum and not limestone. And the issue there was since they had so much free energy, they could desalinate all they want. And then they were discovering that they were flooding their basements. And so instituted drainage wells, and then realized from the amount of dissolved solids coming out of the system that they were melting the subsurface.
Yeah.
So we used well logs to show that this wasn't happening overall. It was being confined to certain horizons. And so they have the prospect of developing sinkholes artificially with their groundwater circulation. Another fascinating issue is the existence of natural siphons. Probably the most famous one is the one under the city of Jerusalem in the famous Gihon Spring, which would turn on and off on a couple-hour basis before it is now so thoroughly infiltrated by leaking sewage that it runs continuously. But at one time, it was an intermittent spring that provided water for the city. So there are some really interesting things that can happen with karst, even in some very ancient systems where you have silica being dissolved in old fault zones and having granitic karst providing the basis for your water supply. So I'm always fascinated by what's going to happen next when you start making measurements in a borehole.
Okay, guys, now the frightening stuff. How does flow of water occurs in karst? Because it's kind of tricky. What is multiple porosity? You mentioned in the book. And how, you briefly mentioned, Eve, how the conduits develop and what is their importance on groundwater flow in karst. And is Darcy a lost case for karst? Can we use it at all?
Yeah, well, the main thing to think about with karst is that you can have a laminar flow and non-laminar flow and then turbulent flow in some cases. The reason for describing the triple porosity is you do have some karst aquifers, especially if there's a lot of clay size minerals and impurities that never develop a lot of the larger conduits. And so they will behave more like a typical groundwater aquifer. But then you get the, when you have the pure limestones or the evaporites like gypsum that can dissolve so fast, you'll get whole layers that dissolve out. But you also, and you get those, when you have those types of formations, you can get these very huge subterranean, fully confined, like caverns, literally caverns under the ground that are, say, 100-meter wide that people scuba dive through. But what we have found in some of the systems is that these are actually stay in laminar flow a lot of the time at your lower flow periods and only go turbulent during storm events. And so you can actually still use regular groundwater flow equations for average conditions. Those will work. And the reason for a triple porosity definition is there are these units that were burrowed by different critters in the subsurface, and the critters may die and leave these interconnected boreholes that are maybe these small pore sizes. And you've got two instances of this that get sort of frozen in time. You've got where it's a bit of a mudstone, limestone, where the burrows stay intact, and in some cases there are formations where there's shrimp burrows, the shrimp are gone. So you have these interconnected vugs that are can be extremely transmissive. I mean, they'll lots and lots of water, but turbulent flow happens at very low Reynolds numbers, more like porous media, whereas these huge 100-meter subsurface caverns, those behave more like pipes, and so they will go to turbulent flow at a much higher Reynolds number. And of course, in the book we send you to a video that shows a scuba diver in one of these huge caverns in Florida. And of course, they don't enter these caverns through these huge spring openings unless it's laminar flow. If it was turbulent, they'd be thrown out, and you can kind of tell it's laminar, and that when you watch the bubbles come up from the scuba diver, they just sort of float vertically up. They're not spinning around in any eddies. And so we have found that you can use, for average conditions, which often for water supply problems, you're looking at averages and not short-term storm events. So you can actually still use the concept of Darcian or laminar flow. Even surface water can flow laminarly. And most surface water problems, actually, there's something called steady flow. So a lot of surface stream flow, it's actually steady. So it stays sort of uniform, even though it's turbulent, and you can still do a lot with that knowledge. So it's not the end all, but the main reasons for the 3 porosity is that you can have regular porous media type properties within a carbonate aquifer, or you can have this touching vug that's either from where critters dissolved out and the limestone's not that easily to dissolve because it may have some clay content. The other instance of this type of porosity, that where it goes turbulent at very low Reynolds numbers, like porous media, is where you have clays fill in the pores and solidify, and then all the limestone dissolves, and so you don't have like a huge conduit. You just have these smaller openings that allow for a huge high transmissivity, but you'll get turbulent flow at low Reynolds numbers. So that's why we have talk about 3 porosities.
Chuck, anything left for you?
Yeah. Actually, one of the things that people learn in early on in hydrogeology class is, the focus on porous media, and interstitial flow paths between sand and gravel aquifers and things like that. And we call that primary porosity. And then people learn, there's this other thing called fracture porosity, and some people call that secondary porosity or permeability. And that's where the rocks, have broken up. And the thing to emphasize about karst is that karst is a dissolution porosity, and it actually can modify the other 2 types of porosity. And then it forms its own type of porosity, which are the conduits or the cave stream passages. Those are probably the most distinctive feature of karst aquifers wherever they occur. So that's actually important, I think, to distinguish that from primary or interstitial porosity, fracture porosity. It's a 3rd type of porosity that develops wherever there's dissolution going on in the aquifer. The conduits formed by a very complex hydraulic and chemical feedback process, and it's a competitive process. There has to be a discrete flow path that water flows along, and for the dissolution process to start. And of course, in an aquifer, there's all kinds of flow paths for water to travel through, but the most porous or the most hydraulically efficient flow paths are the ones that will develop preferentially at the expense of other ones. So they'll start controlling the development of what we call a conduit network. And so again, through a very complex process. We summarize this in the book. It touches, on the topic of speleology, which is a very broad, complex topic in and of its own. And we're only able to hit on parts of that in the book, but we do try to summarize the important points of that, how conduits form, and then, some of the influences on them, like the original porosity and permeability in the bedrock units, like geological structural influences and hydrologic influences. All those things work together to form conduits and these karst conduit drainage networks and karst basins, which again is another thing we talk about in the book. So there's a lot of unique aspects to karst, and one of the things that's really interesting and unique about it is, I think it's the only type of aquifer that is sort of living. It self-organizes, as in the process of conveying water, it actually changes over time and develops in more efficient flow paths, more efficient ways of carrying water. And so it's a really neat type of thing. Again, that continuous change and interaction is really something that makes karst unique. And, we cover, again, those processes in the book.
Okay, well, from a well logger's point of view, the most of the applications we see are water supply applications. And the fact of life is that when you're drilling vertical boreholes, you mostly just see horizontal bedding planes. And those tend to be the features that you investigate the most. And a solution opening on a bedding plane has the problem that it has to support the surrounding earth. So you know that it's going to be in contact over a major portion of the surfaces just to support the overlying overburden. So in that sense, you can often treat it as a thin porous layer supplying water to the well. The problem is the porosity is extremely variable along the throw of that feature. So there's sort of a double problem here. You have a porous layer with a very complicated distribution of porosity, and you have the other part of the system that cross connects these that you are not likely to see because it's very rarely the case that you drill a vertical fracture. It has happened, and I had one particular project where we not only drilled a vertical fracture, but drilled the same fracture in 2 different locations, strictly by random luck. And I argued, long and hard that this site ought to be saved as a future study site, because you've got a 50-meter separation between 2 boreholes that follow a vertical fracture. But it was a contamination site, and the EPA said, no, those holes have to be plugged and abandoned. And so they dutifully were. But when you're drilling to characterize geology, as you often do, the fact of life is you're biased towards seeing horizontal features and you're going to miss the vertical ones. And in a karst system, you have this cross connection problem, and you're sort of denied seeing one part of the system that's the critical connection.
I was going to add one thing. So Fred was talking about.
Please, Chuck.
Fred was talking about properties of karst aquifer that relate to the extreme heterogeneity of it, and that's another aspect, that most groundwater hydrologists or hydrogeologists they are able a lot of times to sort of ignore that. And in karst, we have to be particularly aware of it and actually try to investigate it in all of its ramifications. Conduits are part of that heterogeneity, and that's what makes them important, because they might actually be very small parts of the aquifer volumetrically. Fred was talking about when you drill down through a rock in karst, you might hit a couple of these openings, but so they don't really seem to be taking up that much of the volume of the rock, but they can be very, very important in terms of the hydraulics of the aquifer. In fact, they probably control the hydraulics of the aquifer, and that's what makes them important and unique.
Okay. Well, one of the points that I make it, at least hope I made adequately in the book, is that in borehole logging with flow meters, you're able to estimate the transmissivity of each zone and also the hydraulic head of each zone. And the transmissivity is just the local value, but the hydraulic head really does tell you about what this particular opening might be connected to. If two zones have different hydraulic heads, you know they're isolated. If they all have the same hydraulic head, you know they're likely to be connected and part of the same system.
Yep. Yep. Very good. So generally speaking, what are the approaches for characterizing and monitoring karst hydrology, let's say at a local scale? Because it varies, even in a small scale, and, you know, when you see something close to each other, as you mentioned, you have differences. So what are the approaches?
Sure. I guess I'll go. Well, at a local scale, of course, you're going to pull out all the geologic maps you can find. And I'm not sure what you mean, how big local is. If it's like, say, 100 square miles, you're going to do a lot of some of the things you do for any study on water supply, which is get all the information you can about all the wells drilled in the area, look at the stratigraphy of the area and any geologic maps that are available. But most important, I think, is the flow meter logging. Once you've gotten your mapping with your boreholes to figure out dip, but some of the things you might do at land surface is just map your vertical fractures and their orientation to get an idea of how your limestones are fracturing, because they will tend to follow a pattern. So a lot of times you'll see a local study that has the rosette diagrams that just show how your fracture orientations at land surface, and you might have stuff on aperture openings. And then you're going to, as you go into more detail at a site, you will get into the standard borehole logging, but also the flow meter logging. And we didn't put in the book in-well tracer tests, but that's another tool that can be done where you actually do a tracer test inside the well. Then you often have studies that are related to maybe one spring. And so you're going to do a lot of dye tracing tests to try to figure out what's the source water to that spring. But you basically end up applying almost every standard mapping tool and then some custom mapping tools. Now, Chuck has a lot of expertise in tracers. And in fact, I got him to help with an Alabama study that involved tracer tests. So I'm going to let Chuck talk a little bit about tracer tests right now.
Yeah,
Please, Chuck.
That's important. I was going to say, again, I think whenever you're a hydrogeologist, you have to define your problem, what you're trying to learn and what the problem is. And then you have to start preparing methods to investigate the aquifer based on what you want to learn about it. And I think one of the things that was important for us in writing this book was to try to set it up to where people understand, again, what are the things that make karst unique and how do they differ from other types of aquifers that you learn about typically in school or in professional practice, and therefore get a proper conceptual model in your mind about what the aquifer sort of looks like internally and what sort of things you have to investigate. And those are going to define the types of methods that you want to employ in conducting the investigation. And so in karst, again, a lot of the focus is going to be on investigating that heterogeneity and especially the effects of conduits and where they are, how they're interconnected, what their effect is on the overall hydraulics of the aquifer system. So while you ask, is Darcy a lost case? No, it's got its place. And we use a lot of conventional hydrogeologic tools like water level mapping and well hydraulics tests and so forth. They all tell us something about the aquifer, but then we have to interpret those tests in the light of a conceptual model of karst, and then also collect data that's supplemental to those types of conventional tools. Tracer tests is one of those types of things. You know, most karst hydrologists do tracer tests with non-toxic fluorescent dyes, and they're the things that we really need to use, the tools that help us actually delineate the discrete flow paths through conduits. And so they help us not only confirm the types of hydraulic gradients and the configuration of the of the water table or the potentiometric surface in the aquifer. They help us actually confirm whether those interpretations based on wells are correct. And they also give us the actual real data about what groundwater velocities are in the aquifer and residence times and so forth. So I think it's important that people understand that, you know, there's some unique tools that Karst people have to apply, such as tracer test, spring monitoring that I think you've mentioned. We still use the conventional hydrogeologic investigation tools, but they have to be applied in a conceptual model of what Karst is and what those things tell us about Karst, and then sometimes go that extra mile. And if there are issues that like contaminant migration in the aquifer that really touch on what that distribution of porosity in the aquifer really is, then that's really where borehole methods come into play. Are really, really super important to be able to learn what that not only lateral but vertical change in porosity really is. So a lot of tools that we have to use in combination when we investigate karst.
Very good.
Yeah.
So since you mentioned Fred, I think Fred has to mention, because you mentioned borehole, that's his.
Yeah, and I would say with Fred, I first met Fred because we asked him to use some of his more advanced techniques in the 90s for flow meter logging in a karst area in Texas. I think that was around 1995 or 94, wasn't it, Fred?
Yes, very soon after we invented the heat pulse flow meter.
Yeah, and so Fred was a pioneer in these flow meter logging. Now the heat pulse is better for smaller flows, but the flow meter logging is very, very important in karst when you're trying to figure out which thicknesses at your site have all the flow. And then if you can get multiple boreholes, and you can determine if it's the actual stratigraphic unit. And so the caliper logs, the video logs, and the flow meter logging have been the most useful, and then some of the in-well tracer tests. So Fred, why don't you go and talk a little bit more about the different types of borehole tools unique for karst?
Yeah, there are two basic classes of flow meters to begin with. One is the impeller flow meter, which is basically a propeller on a stick where you measure the rate at which the propeller is turning as a result of the flow. And then there are the high resolution flow meters, the heat pulse, and the electromagnetic. And actually, we very quickly figured out ways to use these high resolution probes in a high capacity boreholes, hundreds of gallons per minute, and have studies showing how their advantages and disadvantages compared to the impeller in these high capacity karst environments. And I guess that it's not really karst, but in Hawaii, where they have lava tubes, we were able to get a good heat pulse flow meter measurements in wells with lava tubes that were producing at hundreds of gallons per minute while they were actually pumping for the municipal well field. So there are a number of applications, but the bottom line is the idea of measuring flow under two different pumping conditions allows you to come up with this a multiple variable solution for transmissivity for each zone and water level in each zone. So you have a way of measuring hydraulic head in individual zones within completely open boreholes, and determining whether these different zones are a part of the same system and how they're interacting with each other. And then you can actually do crosshole tests where you have multiple wells and you turn the pump on and off in one borehole, and then measure how that sudden change in hydraulic activity propagates out through the system. My PhD student at the University of Rennes in France did a wonderful study where he looked at what happens when the municipal water wells in this small town would be turned on and off, and how that hydraulic head difference propagated out. And here was an application where they were worried about saltwater intrusion. And they discovered the problem is really agricultural chemicals, because the hydraulic head indicated that vertical downflow occurred almost instantaneously from overlying layers. So you can really do quite a bit if you're creative in looking, especially with water supplies, where you have a cooperative pumping regime where they will turn on and off they essentially give you the key to the circuit breaker, so you could turn the pump on and off, and then measure how those changes propagate out through the system. A powerful tool, but there's a lot of unknowns you have to take account of to design the test. So it's kind of an iterative process to figure out what happens as the system is suddenly given a hydraulic change, and what do you have to do to make that change occur at a rate that you can actually measure and quantify.
Interesting, quite interesting. So it's you have to interpret it. You need a lot of interpretation when you have the data, because the model will be very important. Quite interesting, guys. What about the basing in a basing scale? Because Karst usually is misbehaved in many times, or maybe most of the times. How do we study Karst in a basing level?
Well, I'll take a shot at that. I think that plays up the importance of doing proper hydrogeologic mapping, and we have a section in the book that discusses that in detail, with all the methods that can be used and what they can tell you. But I think two of the most important methods is just basic field hydrogeology, where you're going out and mapping water levels, but then again realizing that you're in karst and that the flow paths are going to be discrete, and that you need to check and confirm that information when you interpret your water level map by doing water tracer tests. And so that's where we get the idea that karst is sort of misbehaved, because compared to conventional hydrogeologic interpretations, where you learn that usually the topographic basin boundaries also match the groundwater basin boundaries. In karst, that's often not the case. The conduit networks go underneath the topographic divides, and sometimes they don't even follow structural trends very well.
Mhm.
So you can run into all kinds of situations where you expect groundwater to be flowing is not the way it actually flows. And then it can also change under hydrologic conditions, when you change from low to high flow conditions or flood flow conditions, because if karst conduits are developed and they have very complex interconnections, or they're at multiple levels, the changes in the water level in the aquifer can actually change the flow directions of the groundwater. And so tracer tests are the way to confirm that, and try to get a handle on what that misbehavior actually is at a basin scale.
And another thing that actually Chuck has a lot of expertise with is using your geochemical information from springs. You can use natural isotopes and natural water chemistry, but your spring discharge often integrates some of what's going on in a basin. So analysis of spring hydrographs is really useful for looking at diffuse and conduit flow components. And in some cases, we've been able to use a combination of surface water gauging data with specific geochemical signatures, just to get a feel for how much is the groundwater coming into an area that might have multiple springs, like say on the Swanee River, where you've got a very good groundwater surface water interaction and connection within a highly transmissive karst system. Or in Tampa, we've applied it and using just specific conductance, which we could do continuously, and in-member mixing with hydrograph separation. And then there are a lot of studies using some natural isotopes with spring. So the spring discharge and water quality data, along with these tracer tests, can be very beneficial. And doing your tracer tests at low water levels and our dry periods and wet periods is very, very important. We got lucky in the Karst hydrology field methods class in that we were able to conclusively prove that this one spring was the overflow spring, because we happened to have the class occur at one of the very low dry periods. And so all the tracer went to the base level spring, and it was the first time and none went to this other spring that was still flowing at a very small rate. It was getting close to going dry. And that spring, I think, was only, maybe this much higher in outlet. We've got, very high level vertical leveling between this overflow spring versus the base level spring at this research site that we were doing the study. So doing these tracer tests at wet periods, not flood flows, but wet periods and dry periods gives you a good idea of when you have upper level connections that will flow only at high stands and send water maybe to a totally different place than you thought it was going to go from your dry period discharge. And
we have some figures.
Go ahead.
Look, we have some figures in the book that illustrate quite well. And so I think you can pick up these important points about how the aquifer can behave under different types of hydrologic conditions by the figures that we chose to try to illustrate those properties.
Yeah, the book. Yeah, but this is an important thing. Your book is very well illustrated. Even the videos is very good. They're very, very good. I enjoyed it a lot. Congrats for the work. That was very good. So guys, we have two more topics here. Is contamination. Two heavy topics on Karst, contamination and modeling. Okay, let's go for contamination first. Because contamination is hard, remediation is harder, right? And then we have modeling of all that. Who wants to jump first? Fred, you can go. You're being quiet.
All right. I think probably the most important issue is using the flow meter and determining where the hydraulic heads are. In a number of cases, we've been able to look at karst aquifers. Of course, we're dealing with bedding plane producing zones, but there's this some kind of contaminant spill at the surface. We see there are bedding planes that produce water, and find that several of the uppermost bedding planes have exactly the same hydraulic head. And then there's an interval of massive limestone. And then below that level, we can see the effects of pumping from nearby wells, lowering the hydraulic head. And it's very comforting to see that we have what appears to be an effective aquitard that's keeping whatever's in the shallow subsurface from getting to the deeper zones. Probably the most bizarre situation was a site directly over a city's water supply well with heavy metal contamination. And we assumed from the very beginning that we have obviously a vertical head gradient downward. When we finished with the flow meter work, we discovered that the superficial aquifer where the contamination occurs has a hydraulic head in every bedding plane except for one, which is drastically drawn down. And so we now realize that we have pretty much a constant hydraulic head in the shallow subsurface, and there's one bedding plane that's draining everything off to the side through a vertical conduit that we can't see. So it's the hydraulic head message is really important in determining the general geometry of the flow field you're dealing with.
Yeah, and I guess the thing I would add about contamination with karst systems is they are a lot more vulnerable to man's activities because surface water runoff directly can infiltrate into some of these fractures. So that's one thing to think about. We really didn't cover a lot in there except to say that it is more vulnerable to contamination, and that the flow paths, it's very important to try to figure out where they are, but that's very difficult. And so contaminant sites require a lot more investigation. There can be some natural remediation that happens. We've had studies where microorganisms actually start digesting some of the contaminants. We've had some studies of interest in some of this more recent quaternary karst, where they were looking at pathogens from bacteria. And so instead of using dyes, they use small spheres that have the properties of the bacteria, and introduce that into a lake to see if they made it to these production wells and how fast. And of course they did. And so it changed the whole concept of it made unfortunately the water supply people had to come up with a higher level of treatment, but it also made the state want to protect a larger area for that well field. So it's very difficult to determine exact pathways for contaminants. So the main thing to remember is that karst systems tend to be more vulnerable to man's activities on land surface in outcropped area of carbonates or evaporites.
It's a really complex and difficult topic to discuss in a book like this, to summarize. And we tried to summarize that, but I think the point we tried to make in the book, and I want to make here, is that contaminant hydrogeology is where the heterogeneities and the complexities of karst are just so important to make sure that they're properly understood and characterized. And so all of the methods that we presented in the book, can be applied towards that problem of understanding it. And tracer tests in particular are very important, because there's just all kinds of examples. And we cite one, the Walkerton case, which was an E. coli contamination problem in Ontario, Canada, back in the early 2000s, where you get like agricultural runoff and contamination from surface bacterial sources into karst aquifers. They can travel through conduits so fast with little attenuation. And of course, again, they can go in unexpected directions because they're following conduit flow paths. So it's important to try to figure out those flow paths and those actual groundwater velocities. And that's where you can get really into trouble if you just use conventional Darcian sort of based hydrogeologic investigations and don't do the extra studies, the tracer tests, and other types of monitoring that are necessary to really fully characterize the karst aquifer system. And contaminant plumes can be a really nightmare because they tend not to move, as a single sort of dispersed plume with graduated concentrations or concentration gradients. They can split up, travel at different speeds, go one right after the other. They follow very complex pathways through the aquifers. And so, again, you just have to be very careful and use a karst model, keep a karst model in mind. And I think, again, that's one of the values of the book, is that we present all that information that can help you conceptualize and then design studies that, again, can address the particular problem that you're interested in trying to solve.
Well, from a well sampling point of view, then it becomes important to determine not only whether there's a contaminant or tracer at a well sampling point, but where exactly in the well that tracer or contaminant appeared and what feature is it tied to.
Actually, it is what Chuck just mentioned. It's quite important because your book gives us a much better understanding of the whole picture. You can make your model pretty much understandable in a geological and geochemical way, because you tend to think on how the karst aquifer has been formed and how it behaves in many aspects. That was quite, like I said, it opened my eyes for many things. It was quite interesting reading that. It was very good. So guys, how to model then, using mathematical models? How can we do that with Karst? Can we survive?
100%. 100% yes. But like we always say in modeling, garbage in equal garbage out.
Exactly.
And so the bottom line is, you, as was stated earlier, you have to understand what you're trying to use your model for. We actually, in this book, I tried to talk about every type of model, from the simple regression models that are used, the lump parameter models, and then some of the more advanced numerical models. So, and even with the borehole flow meters, you're using a mathematical model to evaluate which parts of the borehole are contributing flow, how much, and what the heads are. But, commonly we use regression models from the simplest is just to get what we would call a rating curve for an individual spring. You could think of that spring as being similar to an orifice plate for measuring discharge. So we've used this technique at many places where we have a nearby well. So measuring stage and continuous stage in a well is very easy to do. And you can relate that to a discharge by developing a rating curve where you measure the spring discharge and then you develop the curve. So that's very similar to an orifice plate type measurement. So those types of models are used very successfully. And if you've got a well near a coast that's tidally affected, you can often use the tidal data, an actual tidal gauge with your a nearby well, and get fairly accurate continuous spring discharge data that way. So that's a very simple example of a mathematical model that 100% works great. You do need the full range of flow. Then you can get into the lump parameter models. People don't realize that most of a lot of the geochemistry models for even your standard isotope data are lump parameter models. So you might have a piston flow model. Some of them are, like in the book, I show an example that's really old. These have been used forever, but these involve just an ordinary differential equation where it treats each basin within the system as tanks, and you can actually get those to calibrate fairly well. And they have been used for many purposes, both for geochemical analysis to estimate age dates, or for just in the case of the example we show, since the focus of the book was more for water supply, each tank represented part of the basin where there's an estimate of the recharge that goes into that part of the basin, and we know the pumpage in that part of the basin, and they had a one well water level, and they used all of those to help figure out the flow at one of the major springs. And this was used to help look at times where you might have to import water because you were required to maintain a certain minimum flow at this spring. And so by creating the model that fit all the historical data with this lump parameter model, and it actually can run in a spreadsheet. And then they used something called stochastic statistics to try to generate many scenarios of future recharge with pumpage demands to estimate how often they'd have to import water. So that's an example of a model that was very useful, that ran fairly quickly, that was used in a water supply case to help estimate how often and how much water they might need to import during dry periods. Then you've got your full-blown distributed parameter models where you try to model a whole system. And in general, those are successful when you're looking at average conditions. They rely on the groundwater flow equation. Yes, it can be laminar, but as I said earlier, a lot of times in average periods, you're not getting the turbulent flow lasts for shorter periods. And so they're based on mass balance. So if you've got good estimates of all your spring discharge from your system, your pumpage from the system, and you've done a lot of work on your framework to know where and the dimensions, all the dimensions of your permeable units that provide most of the flow, then these models actually are fairly successful for average water supply conditions. But we have seen where you want to go with a hybrid model, takes a lot more numerical effort, and they can be very difficult to get a large one to converge. And they may not be necessary for average conditions, but if you are trying to match your actual storm flow hydrograph where turbulence becomes very important, you won't match it with a simple porous media model. But we actually did a variation of mod flow that allows you to have turbulence flow simulated by adjusting your Ks in a layer. And if you have high K values where you know you've got conduits, you do get the effect of the drop off on discharge as you go into turbulent flow. And so you can still mimic, sometimes you can mimic that turbulent flow pattern with a equivalent porous media model with turbulence turned on. But the bottom line is you really have to tailor what you're going to do based on the problem you're trying to solve. Now, there's much less success with contaminant transport modeling because, once again, it's so difficult to characterize all the details of the heterogeneities. When you're doing water supply problems, you can kind of have things lumped and still get your mass balances to work out. And you don't have to know all the details of where everything is really super permeable. You do have to have some idea to have something that will work. But so there's so many different types of, when you say mathematical model, there's so many of them that, yes, there's plenty that you can use and people do use for either their geochemistry or a simple discharge at one spring, or looking at even some of your lump parameter models where you're looking at matching your observed data to an outcome. So you've got your input parameters. It can just be a statistical simple linear regression, or it can be a curve like a unit hydrograph, or it can be a statistical function like a gamma function that you transform it, sum these together and get an output. And there's even been neural networks used in the same way as some of these statistical parameter models. And they can actually do a very good job of having some inputs that are good, like your recharge and pumpage, duplicate, say, your spring discharge that you want, or your spring water quality. And the main thing to remember when you're using these statistical or lump parameter models, if you want to use it for prediction, you can't use it outside of the range of the values you calibrated the model to. And that's true with any model. But I would say that you have to use care, and there's no point in going to a full-blown distributed parameter model if you haven't done all the characterization and the field work and have some tracer tests. And you absolutely cannot do any transport with a distributed parameter model unless you have some tracer test data, because that's how you're going to estimate that actual rapid flow, is you use the actual tracer test to give you a porosity value so that you can match that travel time. So I hope that sort of, being a person that's done a lot of models and also spent a lot of times, sometimes we spend 5 years characterizing a regional system. And then, and we're modeling all along, but the goal was just to see if our concept of how the system works is correct with the distributed parameter model, because that synthesizes all the data you've collected all for those years and helps you understand the system more. So, but it takes a lot of experience and time, developing models that work. It just takes a lot of time to really get the right data and experience. It helps to understand the math, but you also have to understand the geology. So you really shouldn't even bother doing, you're not going to be able to calibrate or develop a really good model unless you've got some data, but you also may want to use it in a circular fashion where you collect data, you get a conceptual idea of how you think the system works, then you try to put it in a mathematical model and see if that works. And if it doesn't, that helps you figure out where you need to collect more data to improve your understanding of the system. So it's really goes, you have to do all of it. You can't do a model with no knowledge.
Yeah, that's true. And I thought it's interesting that it could fit on ModFlow, because how high was the K that you could use? Because that would be a mathematical challenge, I think.
Yeah, with the biggest problem we've had, I helped develop that conduit flow process for ModFlow. Because we wanted it, but that's where me and Keith, I used a method Keith had used for simulating turbulent flow in a borehole to create that turbulent within a layer without a hybrid model. So I borrowed from what he had done to create that mode, well, we called it mode 2. So mode 1 was the hybrid model where you have a one-dimensional pipe network in a three-dimensional space that leaks back and forth to your ModFlow layers. And then we allowed turning on turbulence within just a ModFlow layer. And you do run into numerical problems with some of your, what we call a standard ModFlow model, where you've put in, if you know where your conduits are, your K values, the hydraulic conductivities, are set very high in those areas where they're conduits. And I have some journal article and some other things that give guidance on estimating a K based on what your knowledge of your porosity and whatnot. But what we have found is that you do run into convergence problems with ModFlow. And I could go into the linear algebra as to why that is, but I think most people's heads would blow up. But the bottom line is, when you have a K of 10,000 next to a K of 10, you're going to have a numerical problem in that system of equations.
That's exactly what I was asking.
Yeah. So, and so what happens is you have to kind of, sometimes you just can't put in, like I estimated through the theory of what the laminar K should be given the conduit sizes for the Woodville-Karst plane, because I had all that data. And the model just wouldn't converge on the really high storm set where we're pumping all this water through the conduit, and it just, it wouldn't work with that high of a K. So I ended up having to use a lower K and still getting everything to work out. So yes, you can have numerical problems with standard ModFlow when you're putting in high Ks where they're conduits.
Good, thank you. Guys, you want to add something? Chuck? All right.
Oh, that's okay.
You're fine. Guys, I think our time is up here. It was really, really good listening to you guys. I'm a hydrogeologist. I love it. and now our audience is all made out of, hydrogeologists. So I hope that they enjoy as well. Guys, could you please make your final statements? I would like to congratulate you for the great book. I really learned a lot from the book. I'm not, just trying to be a salesperson here. I enjoyed it. For sure, right? I really enjoyed it, and I recommend for people. I recommend to my students because it's quite interesting. We can, it's all organized. It's hard to find this material of Karst all in the same spot, right? You have, those editor books where everybody adds a chunk, but it's not all connected like it is put in your book. So you have a wonderful job. Congratulations, and thank you for doing this. Please make your final statements. Eve, you can start again.
Well, I hope I didn't ramble too much because I really do love the topic, and I love to mess around with numerical models of every type, and I do actually really enjoy Karst, and so I hope that people do enjoy the book. And I have to say it was a real effort to get this done. It took a lot of work, and there's a lot of figures in there. We were pushed into putting lots of figures.
I read the first version. I was one of the the reviewers that was pushing for that. That was, but it was very good at the end. It was a very good book. I really enjoyed it.
Well, and I have limited tools right now since I retired and I'm an emeritus. I had Paint and PowerPoint, and that was about it. So all the figures were like, oh God, they want us to add more. But no, they were very helpful. And I really, really want to thank Chuck. Chuck really stuck with this the longest and hardest. We've known each other for many years, and I have a high respect for Chuck, especially in regards to mapping and the field methods and tracer tests. And Fred I've known for many, many years also, and he's just a great geophysicist, and so is John Williams. So they had contributed to the geophysics portions of the book. And I'm glad you liked it. That makes me feel good.
Oh, I'm very sincere. I loved it. I loved it. You, Chuck.
Yeah, we definitely appreciate that compliment, because there were times when we were working on it where Eve and I were going, we don't. It's hard to keep on track. I just wanted to say that we wrote it with a particular purpose in mind. I mean, I don't know who said it, but a long time ago I heard this saying that Karst is kind of like the Disneyland of hydrology, in that it there's all kinds of wild, amazing things to see, and it can take you on some pretty crazy rides. And
that's what I would add. Yeah,
right. So the thing is, as hydrogeologists, there's often a tendency to go, "Oh my gosh, it's Karst. How do I understand it? What are we going to do about it?" And what we tried to do is show, explain that Karst, it makes sense if you can understand it.
Yeah.
You know how it's different from other types of aquifers. You know the tools you need to apply or can apply to understand it. It's not some mysterious, impossible to describe type of hydrogeologic system. You actually can investigate it and get answers that you need to do your work. So we tried to write this with that overall concept in mind. So hopefully it will be really useful to students and everybody practicing hydrogeology and karst and limestone aquifers.
It will, for sure. Thank you. Fred.
Well, as someone who's applied borehole geophysics to the full range of problems in hydrogeology, I can say that karst is just like any other hydrogeology, except much more so. Whatever the problems you encounter in hydrogeology, they're just quantitatively much more complicated, but basically the same idea.
Yeah, water flows downhill.
Yeah.
All right, guys, thank you very much. It was fun having you here today. I enjoyed the book and the talk with you. That was very good. Thank you very much.
Okay.
Bye.
Bye.
Thank you.
Thank you.
Bye-bye.